Now let's move on to the urgent warning about the possible dangers of artificial intelligence. Top experts and executives in the field say it represents the risk of extinction, comparing it to pandemics and nuclear war. Have you ever looked up at the night sky and wondered about the mysteries of the universe? What if I told you that the answers to those mysteries could be found at the intersection of artificial intelligence and quantum computers? It's a captivating thought, isn't it? The combination of these two innovative technologies has the potential to transform our world in unimaginable ways. But with great power comes great responsibility. Let's imagine an intriguing scenario. The United States government forces the development of quantum computers to stop due to an alarming event. Google achieves quantum supremacy by outperforming a standard supercomputer on a specific question. Michio Kaku warns about the dangers of merging quantum computers and artificial intelligence, highlighting the lack of moral conscience of quantum chatbots. The intervention of politicians triggers a disaster. What happened to justify this dramatic response? In our quest to understand quantum computers, we discovered that they operate on the principles of quantum mechanics. They use quantum qubits instead of bits, allowing them to be in multiple states simultaneously thanks to superposition. This property gives them great power to explore multiple possibilities at the same time. The history of quantum computers dates back to the 1980s, when Richard Feynman proposed the concept of quantum computing. Although it sparked interest, it was in the 1990s that significant advances were made in this field. In 1994, Peter Shor presented a revolutionary algorithm for quantum computers that could factorize large numbers, challenging modern encryption methods. This generated excitement in the field of quantum computers in the following decades. The researchers explored different approaches and demonstrated the feasibility of quantum computing using nuclear magnetic resonance. Advances in the development of qubit systems have allowed more complex quantum computers to be built, unlocking their potential for sophisticated calculations and simulations. In 2013, Google and NASA collaborated on the development of the D-Wave 2 quantum computer, but the project was threatened by the impending government shutdown. This created a race against time to ensure the future of the project. Google found itself in a perplexing situation after the closure of its quantum artificial intelligence laboratory. Despite having access to a working quantum computer, they remained silent about its operations until the situation was fully resolved. The government shutdown affected progress and made researchers' work more difficult. In 2019, Google made a major breakthrough by achieving quantum supremacy. Using their Sycamore quantum processor, they successfully solved a complicated mathematical problem, demonstrating the enormous potential of quantum computers in specific tasks. This achievement inspired other large technology companies, such as IBM and Microsoft, to intensify their efforts in developing quantum computers, sparking competition for more powerful and reliable systems. The researchers faced the challenge of decoherence, which causes errors in quantum systems due to environmental perturbations. They developed error-correcting codes and fault-tolerant techniques. In 2020, IBM introduced the IBM-1 system, the first fully integrated quantum computer designed for commercial use, marking an important step toward the accessibility and practicality of quantum computers. The growth of quantum computing attracted funding and establishment of research centers and quantum laboratories, promoting collaborations between academia, industry, and government agencies. Advances in quantum computing raise questions about the existence of extraterrestrial life and the Fermi paradox. Tipler's conjecture suggests the use of black holes as quantum computers by advanced civilizations. The possibility of self-destruction of civilizations before reaching interstellar travel is also considered. The search for extraterrestrial intelligence is not limited to radio signals alone, and it is important to explore other possibilities to increase our chances of success. An interesting study by Gia Dvali and Zaza Osmanov proposes the use of large-scale quantum computing as a technological signature. Black holes could be used as computing sources by extraterrestrial civilizations, artificially creating microscopic black holes. These black holes would emit intense radiation, including Hawking radiation, which could serve as a sign of the presence of advanced civilizations. The radiation would be composed of subatomic particles, such as high-energy neutrinos, which would carry information that is difficult to filter or obstruct. These neutrinos could originate from both Hawking radiation from micro-black holes and the particle collision factories used to create them. The use of the Ice Cube Observatory in Antarctica is proposed to detect these technological signatures by capturing traces of high-energy neutrinos. This could indicate the presence of advanced extraterrestrial civilizations. The lack of detection of these technological signatures raises the possibility that advanced civilizations have surpassed radio communication and digital computing, using black holes as quantum computers. Michio Kaku, a prominent theoretical physicist, highlights in his book Quantum Supremacy how quantum computing can improve the precision of artificial intelligence systems. However, he also points out concerns about its control, such as deepfakes, misinformation and biases in AI models. Scientists face challenges in creating functional quantum computers, with two main approaches: gate-based quantum computing and adiabatic quantum computing. In gate-based quantum computing, individual qubits are manipulated to perform calculations. Scientists are developing new stable qubits, such as superconducting circuits and trapped ions, and are also researching reduction and error correction techniques. Adiabatic quantum computing gradually evolves a quantum system toward a final state that represents the solution to a problem. Phenomena such as quantum annealing are used to optimize complex problems. Various specialized materials and devices are being explored to improve the performance and scalability of adiabatic quantum computers. However, there are numerous challenges on the path to quantum computers. Quantum systems are extremely sensitive to their environment, which can cause errors and disturbances. Finding ways to maintain the quantum coherence needed for computing is crucial. In addition, quantum computers require highly controlled and isolated environments, with ultra-low temperatures, which adds complexity in terms of engineering. Error correction techniques and collaboration between different entities are essential to overcome these obstacles. Quantum computers have enormous potential despite the challenges. They can revolutionize space exploration and the search for extraterrestrial life. With their efficient simulation capabilities, they can improve our understanding of galaxies, black holes, and the origin of stars. They can also optimize spacecraft trajectories, allowing for more precise and cost-effective missions. Additionally, quantum computers can process large amounts of astronomical data quickly, making it easier to discover patterns and anomalies in the cosmos. Another important aspect is the security of communication in space missions, where quantum computers offer significant advantages. Through quantum cryptography, they can ensure secure communication channels and generate unbreakable encryption keys. This strengthens communication between spacecraft, satellites and ground stations, protecting it against possible cyber attacks. Additionally, quantum computers can play a crucial role in the search for extraterrestrial life. By analyzing large volumes of data simultaneously, they can help identify possible patterns or signals of extraterrestrial intelligence. This increases our chances of detecting and potentially communicating with alien civilizations, should they exist. The era of quantum computers opens up exciting new possibilities in our pursuit of knowledge and space exploration. Quantum computers also have a broad impact that goes beyond space exploration. In fields such as drug discovery, materials science, finance, and climate modeling, these powerful machines can revolutionize our approach to complex problems. By simulating complex climate systems, they provide deep insight into climate dynamics, resulting in more accurate weather forecasts, climate projections, and environmental risk assessments. This facilitates the development of effective strategies to address climate change and protect our planet for future generations. However, it is important to address concerns related to safety and ethics. Space has always been fascinating to people as they observe the sky. Scientists and philosophers alike have pondered life's deepest questions. What would it be like to go to distant galaxies and, more importantly, what kind of life might exist there? Space is just space. Its size is absurd. It would take years to reach our nearest neighboring star, even if we could travel at the limiting speed of the universe. At least we have science fiction like Star Trek to test the human imagination, although we have not yet found the answers to these problems. But today, thanks to NASA's warning system, the final limit could be within reach. Since nothing can move faster than the speed of light, this is the fastest it has ever been. Light can reach the moon from Earth in just over a second due to its speed of 300,000 kilometers per second. In less than the blink of an eye, light can travel from Los Angeles to New York. Proxima Centauri is the closest star to Earth, separated by 4.25 light-years. The Parker Solar Probe, which is currently in orbit, is the fastest spacecraft and reaches a maximum speed of 450,000 meters per hour. At that speed, you could get from Los Angeles to New York City in just 20 seconds, but the solar probe would need about 6,633 years to reach Earth's nearest neighboring solar system. Why can't we use conventional rockets? Conventional rockets are ineffective because they are too slow to travel between stars. The distances in space are enormous, and conventional rockets cannot reach speeds high enough for practical interstellar travel. Spacecraft, such as the Space Shuttles and Voyager probes, are limited by their current speed, which is very slow compared to what is required to reach other stars. Even the New Horizons probe, which traveled to Pluto, would take tens of thousands of years to reach the Alpha Centauri system if it were pointed in that direction. Faster than light travel, which would be necessary for convenient interstellar travel, is currently only possible in science fiction with concepts like wormholes and warp drive technology. Star Trek writers ran into problems developing the series due to its space opera nature. They wanted to avoid making the series boring or conventional, so they needed to find a dramatic way to transport the characters through the universe while still maintaining some fidelity to physics. The biggest challenge was the enormous distance between galaxies, which even at the speed of light would take hundreds or thousands of years to travel. The solution came with the introduction of warp velocity, which allowed faster-than-light travel. To justify this, Newton's third law of motion was used, which states that there is an equal and opposite reaction to every action. This law explained how a ship could move at such extreme speeds. When you accelerate in a car or fly in an airplane, you experience Newton's third law of motion. You feel pressure on your seat as the vehicle moves and pushes you against the seat. This is similar to what happens on the Star Trek Starship Enterprise. However, if the ship were traveling at near light speed, the people on board would be crushed due to the difference in mass between them and the ship. To solve this problem, we turn to Einstein's theories about space and time, which allow us to overcome the limitations of the speed of light. According to Einstein, the speed of light is constant for all observers, and time is relative, meaning it slows down as you approach the speed of light. This has been demonstrated by experiments with atomic clocks on fast rockets. For the crew of the Enterprise, time would pass more slowly, allowing them to travel cosmic distances in a reasonable amount of time. However, they still face the challenge of staying in sync with Federation time to manage an interplanetary civilization. The ship needs to travel faster than light to be efficient in its space travel. According to Einstein's special theory of relativity, traveling faster than light is not possible. However, the general theory of relativity provides us with a different perspective. In this theory, space and time can be influenced by gravity and distorted. If we could control space-time and create curvature, we could avoid the need to travel at the speed of light. The Enterprise in Star Trek uses a warp drive that generates a warp bubble around the ship. This allows the ship to move locally at modest speeds while distorting space-time, maintaining synchronization between its starting point and destination. Although in our current reality we cannot curve space and time, in the fictional world of Star Trek, This technology is possible through the use of a compound called dilithium and a curvature engine. The ship and its crew are protected by this curvature bubble as they navigate through space. In 1994, physicist Miguel Alcubierre proposed the idea of compressing spacetime in front of a spacecraft and expanding it behind it, which would allow travel at speeds faster than light without violating the rules of relativity. However, this theory has an important limitation. It requires negative energy or mass. Negative mass is hypothetical and has not been observed, so the only option would be negative energy. For a warp drive to work, a massive amount of negative energy would be needed. Alcubierre estimated that it would require the mass of the entire observable universe to create a 100-meter bubble using its curvature engine. Subsequently, scientist Chris van den Broek demonstrated in 1999 that it would be possible to reduce energy requirements dramatically by increasing the volume inside the bubble, while maintaining a constant surface area, but it would still be much more than is feasible with our current technology. In recent research, methods have been proposed that could bring warp engines closer to reality in a futuristic environment. Additionally, NASA engineer David Burns has developed a design for an engine that he claims could reach speeds of up to 99% of the speed of light without using fuel. Burns uses a thought experiment with a box, a weight, and springs to demonstrate his idea. Although there are limitations due to the principle of conservation of momentum and special relativity, there is a possibility of achieving momentum using ions instead of a moving weight. These advances demonstrate the potential for human ingenuity to overcome seemingly insurmountable obstacles in the future. The Burns helical motor is an expanded spring-shaped design that accelerates ions in a loop to produce thrust. Although the idea is impressive, it presents significant practical challenges. The helical design would require a considerable size of 656 feet long and 40 feet in diameter, and a large amount of energy would be needed to achieve significant thrust. Although the process is inefficient, in the vacuum of space it could work if enough time and energy is available. Although not everyone shares Burns' vision, there are many people interested in traveling to other stars. Although achieving this goal may be difficult, ignoring all options guarantees that it will be impossible. As the saying goes, 100% of the shots that are not attempted are missed. David Burns' helical engine is a major advance in space exploration. Although it is mainly theoretical and faces practical challenges, it could be crucial in unlocking the secrets of the universe and opening up new possibilities for exploration. Although we do not have the detailed plans to build a functional engine at present, the future remains promising. Creativity and perseverance will allow us to continue pushing the limits of space flight and discover new frontiers. Humans have a deep connection with the past, so history is very important to us. As a result, scientists devote a lot of time and resources to discovering what happened in the past and how past events shape our realities. Sometimes, however, what they discover about the past is shocking, especially when they encounter parts of the past that are unknown to them and cannot be understood. Some of these cases are huge pieces of the history of the universe that cannot be explained by any modern method. Interestingly, the Earth itself is missing in some parts of its history, and this is one of the deepest mysteries we know. It's like if your high school teacher wiped the blackboard and lost all the information forever, he would never recover. This is known as the Great Unconformity. Using clues from the Great Unconformity, scientists are now trying to unravel the mysteries of the universe's huge missing pieces. The TY or GU is a time gap in the geological record that ranges between 100 million and 1 billion years and is found in various rock sections around the world. What happened was that researchers discovered chemical evidence in the rocks indicating that the GU formed near the end of the Precambrian period, between 850 and 680 million years ago. On a much larger scale, the cosmic microwave background cold spot or CMB is a huge gap in the history of the universe that scientists are trying to explain with different, interesting theories. Significant events in time and space leave indelible marks on the universe. The Big Bang, the cataclysmic event that gave rise to our universe 14 billion years ago, undoubtedly left its mark on everything we see today. However, the most lasting imprint is the CMB, the primordial microwave radiation that fills the universe. Our newborn universe was a hot, dense plasma filled with nuclei, electrons, and photons. After several 100,000 years, the universe cooled and neutral atoms, such as hydrogen, began to form, allowing light to spread. This gave rise to the CMB, which has cooled and expanded to a microwave wavelength of 2.7 Kelvin. Although it appears uniform, there are small temperature variations in the CMB, which are the result of early quantum density fluctuations in the universe. These variations are the reason why some regions of the universe are more densely populated than others. The universe has densely populated regions that affect the redshift of light traveling through them, while less dense regions affect the blue shift. This is reflected in the temperature variation in the CMB, which helps us understand the large-scale structure of the universe. There are two types of Sachs-Wolf effect, the ordinary effect and the integrated effect. Fluctuations in the CMB support the theory of cosmic inflation and allow us to calculate the amount of dark matter and energy in the universe. The CMB has provided scientists with much data since it was predicted in the 1940s and experimentally detected in 1964. However, it has also revealed puzzling mysteries and anomalies, such as a significant discrepancy in the CMB observed in the two opposite hemispheres of the planet. Darling, the most intriguing mystery concerns a large and exceptionally cold spot in the microwave background radiation that spans more than 1 billion light-years. The CMB cold spot is a cold, anomalous zone in the microwave background radiation that was first detected by NASA's Wilkinson and Microwave Isotropy probe, and later confirmed by the European Space Agency's Planck satellite. Although it is thought to have been caused by primordial density fluctuations, this is unlikely as it is much colder than would be expected from a Gaussian distribution. Researchers have proposed various theories to explain its origin, including the presence of a cosmic supervoid between us and the cold spot. Galaxies have less matter density in cosmic voids, while superclusters have more galaxies than average. It has been proposed that a supervacuum in the direction of the cold spot and the cosmic background radiation could explain this phenomenon. Some scientists have claimed to have discovered such a gap, but subsequent studies have ruled out its existence. Other research suggests that a vacuum massive enough to explain the cold spot would be an anomaly in the standard model of cosmology. A team of astronomers has identified a large single structure in the region measuring 1.8 billion light-years across. A relatively nearby supervacuum was discovered using optical and infrared observations, which could explain the cold spot of cosmic background radiation. Supervoids and superclusters have an impact on CMB photons. Photons passing through a supercluster are heated and photons passing through a supervoid are cooled. It was found that even this large supervoid does not fully explain the temperature drop of the CMB cold spot. One study used spectroscopic data to investigate the redshift of galaxies in the line of sight of the cold spot. The researchers performed a control measurement and found 3 voids and possibly a 4th, but these were not large enough to explain the cold spot. They concluded that the cold spot was most likely caused by primordial density fluctuations, rather than voids. It has been proposed that the unusual motion of galaxies in the region could be responsible for the cold spot, and one study found 19 dwarf galaxies lacking dark matter, suggesting that their lack of dark matter was not caused by interactions with other galaxies. Dwarf galaxies can affect other studies that rely on dark matter, and whether this also applies to the CMB cold spot will be investigated. Different theories have been proposed to explain this stain, but more observations are needed to validate them. Cosmological observations, such as Type 1a supernovae and baryon acoustic oscillations, must be taken into account to support any viable solution. Some studies challenge our current assumptions about inflation theory and the flat universe, so more research is needed to understand these findings. It has been proposed that the cold spot in the CMB could be evidence of a collision between parallel universes, according to the multiverse theory. However, additional evidence and consistency with other cosmological observations is required to support this claim. The Planck team's most recent findings neither confirm nor deny this possibility. To improve our understanding of unusual phenomena like the cold spot, we need new data from sensitive telescopes and a better understanding of dark energy and how it affects the evolution of our universe. Scientists have confirmed the existence of a large void called the Eridanus supervoid in the cosmic web, using data from the Dark Energy Survey. This void could be a possible cause of the cold spot, an anomaly in the cosmic microwave background. The cosmic web is made up of galaxies, clusters and superclusters that are gravitationally attracted and accelerated away due to dark energy. The supervoid is a cigar-shaped structure that measures about 1.8 billion light-years across and contains about 30% less matter than the surrounding galactic region. The scientists created a map of dark matter in the same direction as the CMB's cold spot using effective gravitational lensing, which warps light due to the gravitational influence of invisible dark matter. This map is the largest ever created and maps dark matter in more than a quarter of the southern hemisphere. The scientists discovered an invisible dark matter underdensity corresponding to the underdensity of galaxies in the cold spot region. A group of 300 scientists from 25 institutions and 7 countries are working together to understand dark energy and its impact on the acceleration of the universe. They use the Dark Energy Survey, which uses a 570-megapixel digital camera called the D camera to document hundreds of millions of galaxies, supernovae, and patterns in the cosmic web. The U.S. Fermi National Accelerator Laboratory oversaw the design of the chamber. For the past 15 years, scientists have been studying how voids in the universe affect the acceleration of the universe. Gravitational forces and the expansion of the universe compete with each other, deepening some of the gaps between galactic clusters. Photons experience an integrated Sachs-Wolf effect, which indicates that there is a net loss of energy in their journey through a vacuum. This effect is known as gravitational redshift. Although the new finding confirms that the Eridanus supervoid is massive, it does not explain the discrepancy between the predictions of the current standard cosmological model used to predict the behavior of dark energy, known as the lambda cold dark matter model, and the observed change in temperature in the cold spot, which can be attributed to the effect of the supervacuum on the CMB photons. The coincidence of these two individually rare structures in the cosmic web and in the CMB is insufficient to prove causality by a scientific standard, but it is sufficiently novel in the long history of the CMB cold spot problem. In summary, there are 2 ways to look at this problem. Either the lambda CDM model is correct, and the CMB cold spot is an extreme anomaly that simply occurs in front of a massive supervacuum, or the lambda CDM model is incorrect, and the integrated Sachs-Wolf is stronger in supergaps than expected. Global efforts are underway to better understand dark energy and its role in accelerating the universe. Scientists are using tools like the Dark Energy Survey to document hundreds of millions of galaxies, supernovae, and patterns in the cosmic web. Additionally, they are investigating supervoids and the dark ages to better understand how the first galaxies formed. Some evidence suggests that dark energy could have a greater influence on the universe and that cosmic expansion is accelerating, raising questions about our understanding of this fundamental force. Neutral hydrogen emits radiation with a wavelength of 20 to 21 centimeters. But as the universe has expanded over the past 12 billion years, those wavelengths have also stretched. According to the authors of the new study, the wavelength of neutral hydrogen has been stretched to about 2 meters, and this is the signal they are looking for using the MWA. The problem is that many sources, both artificial and celestial, emit the same wavelength, and all of these other sources are many orders of magnitude stronger than the signal they are trying to detect. Even an FM radio signal reflected from a plane flying over the telescope is enough to contaminate the data. The scientists developed a set of equations to identify and removed contaminants in their observations. The researchers determined that every 2-meter trace of emissions they found came from somewhere other than the neutral hydrogen they were looking for. After taking more than 1,200 radio wave snapshots of the sky, although the expected atomic signal was not discovered, the new research narrows the scope of future searches for neutral hydrogen. According to the researchers, these findings present a strong case that the MWA experiments are leading this search in the right direction. With more research, the last vestiges of the cosmic dark ages could be discovered. What do you think about the origin of the universe? Share your thoughts in the comments section below.